We've now looked at a variety of schemes for authenticating to some kind of central authentication server. Some of them involving, or most of them involving cryptographic techniques, not all though. But now let's look at distributed systems authentication, where cryptography becomes much more significant and a whole new aspect of cryptography will start to open up. In particular, what I'm speaking about here are cryptographic protocols. And it's interesting and rather curious that a lot of the theory component required for certification exams, like for example the CISSP certification, ask a lot of questions about crypto primitives like AES and RSA and SHA-2 and SHA-3, etc., but almost never ask about the protocols. This is really important because when cryptographic systems break, it's almost always the protocols that break, or the implementation. And of course, the protocols are, in many cases, the implementation. So the protocols are used to specify what should be encrypted, how it should be encrypted, when, at what point in the protocol, and where, by Alice, by Bob, by Carol, etc., in order to satisfy various security properties like authenticity, confidentiality, anonymity, and so on and so forth. Now, we'll look at some simple examples, but I want you to bear in mind that these things can get very, very complex. They're notoriously difficult to design and prove correct. And we'll look at an example of that in the form of the original Needham-Schroeder secret key protocol. But once you get to things like electronic voting systems, which we'll look at in a later lecture, there are competing requirements. For example, you must identify yourself and authenticate your identity in order to confirm that you are registered and entitled to vote. Excuse me. But you want your vote to be recorded anonymously. And so, for example, we talked in talking about digital signatures about blind signing. Having authenticated yourself to some entity like the registrar of voters, you can then give them your vote to sign blindly, and then the blind signed vote can be unblinded, and then you can use that to record your vote without it being associated with your identity, for example. So these protocols can get quite complex, and very often it's very hard to prove that they do operate correctly and don't have vulnerabilities. Now, we'll also find that as we go through the description of the protocols, I'll show you the protocol descriptions, or what are often called protocol ideations, which are the messages that get sent between Alice and Bob. It's the protocols especially that require the cryptographic cast of characters, Alice and Bob and Carol and Trent, a trusted third party, Peggy the prover, Victor the verifier, and so on and so forth. And you see the messages that go between Alice and Bob to Alice and Bob to Trent and so on and so forth. But it doesn't show what happens inside these principles. What are they looking at? What do they check? And at what point do they say, this is not working, the protocol is failing, I'm going to abort this, I'm being attacked, for example. So there are various different types of protocols. There are what are called arbitrated protocols. And the arbitrated protocols rely on some trusted and assumed to be completely disinterested and fair third party called Trent to arbitrate the protocols. And they're often used by mutually distrustful protocols. They're a bit like lawyers and courts in the real world. Generally speaking, you may, for example, I've seen reference to this when we talked about digital signatures. Some of the signatures might send a signature to the third party who will only verify or validate the signature if it's required, for example. There also are what are called adjudicated protocols, and these are a subset in which the arbitrator is usually not involved unless the parties disagree, and then they will turn to Trent, the third party, to arbitrate and adjudicate whether the protocol ran fairly or not, and what the different parties can rely on. But generally speaking, in a very, very large distributed network like the internet, where there are billions of participants and more coming online because of the Internet of Things, for example, we don't want to rely upon central arbitrators or adjudicators. Instead, we want the protocol to enforce the correct behavior on the various parties. Either they do the right thing or they don't, right? The protocol stops and nothing else happens after that point. And so we prefer the self-enforcing protocols these days on the internet. Now, we've talked earlier about various different kinds of protocols. Man-in-the-middle attacks, like Alice talking to Bob, but Mallory is in the middle. We talked about reflection attacks, in which you bounce messages back at a participant. There's Oracle, where you actually send stuff to a participant, and they then send you back a reply which has done something to what you sent, perhaps signing it for you or whatever. Replay attacks, which capture a message and then reinsert it later. And there are various more complex, what are called interleaving attacks. So looking at authentication, the simplest form of authentication is what we discussed previously. Logon authentication, using a passphrase and using a one-way function to store the hash. Okay, so Alice sends to a host the password. Now the password is being passed as plain text. So this is clearly vulnerable to sniffing and replay attacks. Anybody who captures the password can just supply the password in the future and the host will accept it. And so that's a very, very weak form of protocol. And that's the protocol that was used in, for example, original Telnet and FTP protocols on the internet, and it's the reason why we don't use these things today. There are modifications of that, for example, in classic old school Windows networking, where you'd log on to your computer, give it your password, and it would then hash it and send the hash over the network. Why they thought that was better, I don't know, because passing the hash is vulnerable to sniffing and to replay attacks. So that's going to work. So let's look at a simple example, the wide-mouthed frog. Okay? This is the simplest secret key, or symmetric, authentication and key exchange protocol. It's developed in the days before the use of public key cryptography, before it was invented. So what happens here is there's a trusted third party called Trent. And Trent shares various keys with Alice and Bob. Okay, so the protocol starts with Alice sending to Trent. Alice, A, that's my name, and then she assembles three components. Okay, there's a timestamp at A, there's the name of B, and there is a key value. It's going to be a session key. Okay, she generates it as a cryptographically secure random number. So she takes those three components, concatenates them in some way, and then encrypts the whole lot using her secret key. It could be a DES key, would have been back in the days when this was first noised, or these days it could be an AES 128 key. And both Alice and Trent know that shared key. So she sends that to Trent. Now that effectively is Alice saying to Trent, I'm going to want to talk to Bob, to B. Okay? And here's a timestamp. And here's the name of the person I'm going to talk to, and here's the key that I want to use to talk backwards and forwards. So she trusts Trent to relay this. Now Trent can't do anything, nor can anybody else, unless he knows Alice's key, which he does. And so he decrypts those encrypted components. He finds the timestamp, okay, checks that it is a recent timestamp. He then looks at the name of the party she wants to talk to, which is B, and he takes out the key, K. And so he turns around and recreates a message to send to Bob, to B. And in it, it contains a timestamp, it contains Alice's name and a key, and this is all encrypted using Bob's key, which Trent also knows. Now, when Bob gets that, he realizes it's encrypted with his key, and so he decrypts it. He's willing to believe it came from Trent because Trent's the only other party that knows his key. And so he checks the timestamp that he gets out of it, checks that it was recent, and he then realizes it's going to be used it actually contains a session key K, which is going to be used to talk to Alice A. And so now from this point onwards, okay, Alice and Bob both share a session key K and can start to use it to then communicate backwards and forwards. So notice, both TA and TB are timestamps. And I asked the rhetorical question, what would be possible if those timestamps weren't there? I'm going to leave this as an open question for you to think about. We might discuss it in a workshop, for example. What could an attacker do if those timestamps weren't in those encrypted packets? And we also have this assumption that K is a cryptographically strong key, right? It is a genuinely random key. Otherwise, there's not much point, because every time that Alice starts generating keys, if they're related in some way, Bob can guess what kind of key value Alice will next generate to talk to Carol or Dave or whatever. So that also is a possible weakness, but it's not in the protocol itself. You should always document the assumptions you make. Now, this protocol has its weaknesses. And in fact, in the days of secret key or symmetric cryptography, prior to the invention of public key cryptography, there was a lot of discussion and work done on developing what are called key exchange protocols. Because after all, we discussed earlier the key exchange problem. If Alice wants to talk to Bob, how can she get the key that they want to use to Bob? That's what this protocol does. It mutually authenticates Alice and Bob and transmits a key between them, K, that Eve, the eavesdropper, can't figure out unless she knows Alice's key or Bob's key, which she won't in a proper, well-developed system. So there was lots of discussion about this kind of problem and the vulnerabilities and weaknesses that the various protocols had. One of the protocols that emerged towards the end of this period was a thing called the Needham-Schroeder secret key protocol. It's a very important protocol, and it still lives on today with modifications, as you'll see. Now, in this scheme, Alice and Trent share a secret key, KA. That probably should be subscripted in that slide. Bob and Trent share a secret key, KB. So Trent actually knows the various keys. Alice needs to talk to Bob. And there's some properties that are required. First of all, authenticity. Alice needs to know that she's talking to the real Bob, and Bob needs to know that he's talking to the real Alice. So mutual authentication is required. Also, confidentiality. They don't want Eve, an eavesdropper, listening in. And Alice and Bob, it's an assumption here, both trust Trent. And probably, they're both part of the same company, the same network, they part of the same security domain. And so Trent's got some kind of, reasonably, there's a reason why Alice and Bob trust Trent in this scenario. Excuse me. So here's how the protocol works. First of all, Alice sends to Trent a plain text message. It's not encrypted. It's A, B, and NA. Now, in a previous lecture on digital signatures, I introduced the concept of timestamping. And I mentioned, the idea of nonces, these random numbers, which are N once, or nouns they're also called. In this case, we're going to call them a nonce. So it's a random number which Alice generates. So this is simply Alice's name, Bob's name, and a nonce generated by Alice. Now Trent takes this and he realizes that Alice is going to want to talk to Bob. And so in this scenario, Trent comes up with a session key which will be used by both Alice and Bob. It assumes that Trent is really good at this task, and Alice might not be good at generating random numbers because her computer isn't powerful enough, or it's old, or whatever. And so he generates a message. Now, the message is multi-part. First of all, there's going to be the session key, which will be used to communicate between Alice and Bob. That's KAB. And he takes a copy of that session key, and he takes Alice's name, A, puts those two together, and encrypts it with Bob's key, KB. He then prepends in front of that another copy of the session key, Bob's name, B, and the nonce that Alice had sent to him. And he encrypts all of that with Alice's key and sends it back to Alice. Now, upon receiving this, again, the protocol IDH doesn't show what Alice is going to do with this. What does it all mean? What does she do with it? So Alice will decrypt the entire message using her key, and she gets back out the nonce, and she compares it with the nonce that she sent previously. The two match. So that means, right, this is a reply to that message with that nonce number, and it must have come from Trent, because the only other party that knows KA, Alice's key, is Trent. So she believes it's a legitimate reply from Trent, and she knows that it's a key to talk to B, to Bob. It contains KAB, so she's decrypted that. But the next part of the message, the final part of the message, is encrypted with Bob's key. It's a copy of the session key and Alice's name, all encrypted with Bob's key, which Alice doesn't know. So she can't make sense of it. Right? As you'll see later, this is called a ticket. It's just an opaque piece of information that Alice can't manipulate anyway. She can't play around with it. She can just simply, relay it somewhere else. Which is what we typically do with tickets. So Alice turns around and then sends the ticket to Bob. The ticket is this message that contains KAB and A, all encrypted with KB. And so Bob gets that, and he can decrypt it because it's encrypted with his message. Okay? He then, having extracted KAB, then turns around and replies to Alice by taking a nonce that he generates, encrypting it with the session key. So he sends that to Alice. Alice gets it. She realizes it's a reply to that message that she sent in the previous step, and she knows to decrypt it using the session key. Typically, these messages also have other fields around them, like sequence numbers or whatever. So she knows what it is. Certainly in the case of IP, it'll have the IP source address and destination address and what have you. So she knows it came from Bob. She knows to use KAB to decrypt it. And so she gets back out this nonce. And what she does then is to take the nonce value, subtract 1 from it, and then re-encrypt it with a session key and send it back to Bob. When Bob gets this from Alice, he knows now that Alice has got the session key, so this reply must have come from Alice, and she successfully decrypted the nonce that he sent, and decremented it, and then re-encrypted it again and sent it back. You can't decrement 1 from the nonce value without decrypting it and re-encrypting it. Okay, and so this completes the protocol. So NA and NB, as we said, are nonces, random numbers generated by Alice and Bob, respectively. So, when this protocol was published by Needham-Schroeder, everyone thought, that's it, they've solved the problem. Okay, it's really been solved now, so we know that's the way we can go forward. We can use this protocol. It successfully exchanges mutual authentication between Alice and Bob, and a session key gets exchanged between the two. And you'll notice that the session key, KAB, is always encrypted, either with Bob's key or both Bob's and Alice's key, okay, as it's exchanged over the network. So therefore, nobody else is going to know the session key. So far, so good. And everyone breathed a sigh of relief. We've now got a really good protocol that solves this problem. Trouble was, 7 years later, in 1981, Denning and Sacco published an attack on the Needham-Schroeder secret key protocol. Now, I'm just going to let you pause for a few minutes, okay? Look at this slide, maybe pause the lecture at this point, and see if you can see where the vulnerability lies. It's actually in step 3. That's the message that goes between Alice and Bob that contains the ticket. Okay, and another clue, it's a replay attack. Now, I'm not going to give you the answer in this lecture. As I say, it was missed for 7 years by experts until Denning and Sacco came up with it. But I will actually give you the answer maybe in a week or so's time through iLearn. And also, think about how it could be fixed. Okay, I might as well go ahead and tell you now, actually. Okay, the trick is it's a replay attack. If someone, an attacker, has spotted the exchanges between Alice and Bob, which in a previous session were encrypted with some key, KAB, a session key, and has broken that session key, then the attacker can actually just restart the protocol partway through by sending a message replaying that step 3 message, KAB and Alice's name, all encrypted with KB, to Bob. Okay, Bob has no way of knowing this is an old message. It's a replay attack. And so he'll quite happily extract KAB, send back to Alice a nonce encrypted with KAB. Alice will pick up that message, extract the nonce using KAB, etc., and carry on. So it can be fixed by yet another example of a nonce. Okay? What we do is to start the protocol off this way. Alice sends to Bob Alice's name. Say, I'm going to want to talk to you. Okay? Bob replies, by sending back a kind of reverse ticket, if you like, N prime B. Yet another nonce, which is different from the NB that's going to be used later in the protocol. And he sends this packet that contains a kind of a ticket, which is Alice's name, another new nonce, all encrypted with KB. Now, Alice turns around and talks to Trent at this point and sends a message containing A, B, her nonce value, the thing she just got from Bob, this kind of pre-ticket, Alice's name, the nonce value, all encrypted with KB. Now, Trent will get that. He knows it's a request to start conversations between Alice and Bob and generate a session key for them. And he therefore is able to take out, because he knows Bob's key, he can take out that nonce, if he needs to. And what he'll do therefore is generate yet another message. Now in this case, it's going to contain, first of all, the newly generated session key KAB, Alice's name, and the nonce extracted from the previous step, all re-encrypted with Bob's key. And then before that, he puts Alice's nonce, the session key, Bob's name, and then this new ticket, and then encrypts the whole thing using Alice's key. So Alice then gets that back. She can decrypt the entire message, get out the nonce, NA, check that it matches what she generated previously, gets out the session key, gets out Bob's name, and gets out the ticket, and she can then turn around and just send the ticket to Bob. Bob will get the ticket, he decrypts it using his key, extracts the session key KAB, Alice, that's the name the session key is for, and N prime B that he generated earlier, compares it against the earlier value, realizes it's a reply from Trent containing the correct nonce. He'll accept it. So this fixes that. Notice the attacker can't encrypt the nonce, right? There's no way he can deal with that. So I've explained these various different protocol steps as I went through. And it's very clear that trying to think about this stuff is difficult. Okay? Informally reasoning about these protocols doesn't cover all attack possibilities. When the Needham-Schroeder protocol came out, first of all, people thought about it, but it took 7 years to come up with one possible replay attack against it. So there actually are what are called formal logics or calculi. The oldest one's a thing called BAN logic, which gets its name from the authors, Burroughs, Abadi, and Needham. And there also are later calculi, like the theory of communicating sequential processes, the calculus of communicating systems, which is used to analyze protocols in various ways, and a thing called SPI calculus. And there are even more sophisticated protocols these days, really. So let's look at one real-world implementation of this kind of technique. Again, this is using nothing but symmetric or secret key cryptography. Forget all about public key stuff and RSA and Diffie-Hellman and those kinds of things. This was invented before that. Okay? There's a protocol called Kerberos. And Kerberos is very widely used. because in Windows Active Directory, okay, Active Directory really is two things. It is LDAP, the Lightweight Directory Access Protocol, to store directory information about things, and it's Kerberos, okay, with Microsoft proprietary extensions. So Kerberos was created at MIT as part of a thing called Project Athena, which it spun off lots of interesting things like the X graphics protocol, for example, which is what gives you graphical desktops on Unix boxes and the like. Right? And it was intended to provide authentication and message protection. It's a key distribution protocol, derived in part from the Needham-Schroeder secret key protocol. It provides security services to what are called principals, and the principals are people and services like database servers, for example, and those kinds of things. It uses a thing called a KDC. We talked about Trent, the trusted third party. Now, in the Kerberos protocol, and in subsequent protocols like it, like SESAME, it uses a thing called a Key Distribution Center, or KDC. And the KDC actually knows the secrets which are shared with the various principals. So Alice has a key which is shared with the KDC, Bob's got a key, database servers have keys, machines have keys, etc. Okay? The KDC follows a protocol a bit like the Needham-Schroeder secret key protocol to generate tickets, and these tickets allow the principals to authenticate to each other. Now, there are various different versions of Kerberos. What you'll find these days is Kerberos version 4 was designed in the days of DES, and it was a fixed field size binary protocol which had 56-bit fields, which are for DES keys. Whereas Kerberos version 5 is defined in a thing called Abstract Syntax Notation Type 1, which is an ISO standard, and it encodes the various keys and other values being passed around in a thing called Data Extended Representation, which is a SUN protocol, as type length value triplets. And you can interoperate Kerberos 5 and Kerberos 4. Now, where Windows Active Directory has domains, most systems have domains, the same concept exists in Kerberos. They're called realms. Okay, by convention, a Kerberos realm name is just the domain name. It's the internet domain name of a company or a subdomain in uppercase. And each realm is distinct, but actually Kerberos does allow cross-realm authentication as well. So the principals have a key. And in the case of humans, the key is generated from a password or passphrase. It uses a hashing algorithm, a bit like PBKDF2. And it sorts the password or passphrase with a realm name and generates a key from that. The principal names are globally unique and case sensitive. They consist of a username or service name and an optional instance. For service and host principals, it is the fully qualified domain name of the host, or it's the word admin for admin principals. And they just wind up looking like email addresses. So a user could be jblogs@sales.mycorp.com.au. The realm name is always uppercase. Or an administrator might be fry/admin@it.mycorp.com.au. Or a particular machine might be host/sqlserver.mycorp.com.au, which is the fully qualified domain name of the host, at the realm name mycorp.com.au. Now, as I mentioned, there's a hashing function called the string to key function, which actually turns a password into a key. And because you may change your password from time to time, and there may be old versions of keys around in various places, the keys are versioned and actually stores multiple different versions of the keys over time. And as I say, they are salted to generate the keys. Machines don't log on at the keyboard with a passphrase. They just have their keys. And the keys are stored in what are called Keytab Files on the database server or whatever, right? And it's very important that any service principals like database servers and the like should have a Keytab file that's readable only by that service's system account. So a database server would actually have an account on the machine it's running on, and its Keytab file will be readable only by that user. So the KDC is actually two components. It actually has two parts called the authentication server and the ticket granting server. And they share access to a secret key database, as you'll see. Now, actually, the two parts are both part of one daemon process called KRB5KDC. There's also a separate daemon process called KAdminD, which is used by administrators to administer the KDC. And it's also used for password changes, because password changes actually aren't part of the Kerberos protocol, believe it or not. It's done outside. Now, because the KDC is a central, vital component, it's quite common to have slave KDCs that also have copies of the secret database, and they have their own authentication server and ticket granting server. And these slave KDCs actually get their database by running a thing called kpropd, which propagates the secrets from the master KDC to the slave KDCs. So let's look at it in operation. I'm going to take the scenario where, and I'll show you this in the next slide, the user logs on and then starts work and wants to connect to a database. Okay, so in step 1, the user logs on and he gives his username and password or passphrase. And when he logs on, his machine, Windows, desktop, whatever, generates a secret key from that, okay, using this hashing function, and then it caches it in its memory locally at that point. So far, all we've done is given the machine the password or passphrase and generated a key from it. We haven't checked that it's a valid password or passphrase. So this might be a bit different from what you're expecting a protocol would do. So we're going to go through this process. You might want to actually take a look at the PDF version of the slides and get to this particular slide and keep it in front of you so you can see what's going on. All right. We're going to go through the various steps from user logon onwards, right? But you can track what's going on this diagram, and we'll review it again at the end. But as you can see in this diagram, the KDC at top center has these two components, the authentication server and the ticket granting server. And the keys for these things, and for the clients, and for the database service, etc., are all stored in this keys database, which is accessible by both of them. So, in step 2, the Kerberos client on the user's workstation sends an authentication server request to the authentication server in the KDC. This is simply plain text. It's not encrypted. It just contains the client's principal identity, the user name, okay, identity, the client local time, so it's got a timestamp to avoid replay attacks, and the ticket granting server's principal name. Remember, the ticket granting server is also part of the KDC. So it's got a principal name, which is krbtgt/realm@realm. Now, I'll come back and talk about an extra complication later. We'll just look at this right now. So, in step 3, the authentication server checks, do I know about this client principal? Do I know this user? Is he in my database? Step 2, does the timestamp match? Are we within 5 minutes of the timestamp that's given in the AS request message? This is to avoid replay attacks. Now, if both of these are correct, if the client principal exists in the database, then the authentication server can extract the correct key for that client principal. It can then go ahead and it will generate a random session key, which will be used for client to ticket granting server communication. And it then assembles the ticket granting server's copy of that session key, the ticket lifetime, which might be something like 24 hours, KDC timestamp time now, and the client's IP address. And it encrypts all of that with the ticket granting server's key. Remember, the authentication server has access to the ticket granting server's key because it's in the key store. All of that's encrypted with the ticket granting server's key, and it's called the ticket granting ticket, or TGT. It then adds on the client's copy of the session key, which will be used for client ticket granting server communication, the KRBTGT's principal name, and the ticket lifetime, and it encrypts all of that with the client's key that it extracted from the database. And it sends that back in an AS reply, authentication server reply message. So, one of two things will now happen. The client decrypts the AS reply message using its key, and it extracts the ticket granting ticket and stores it in the local credential cache along with the session key, etc. Or, if the user gave the wrong password, it'll fail, because from the wrong password, it generates the wrong key. Right? Now, excuse me, notice, the ticket granting ticket is encrypted with the ticket granting server's key, so the client can't manipulate it. That's why it's called a ticket. It's a completely opaque token. In fact, some protocols call this a token that the client can't manipulate in any way. So in step 5, the client now says, connect to a database. To connect to the database, it's going to need a session key and to authenticate to the database. So it constructs a ticket granting server request. The ticket granting server request contains the service principal name, database server host name @realm, the ticket granting ticket, an authenticator, which is a timestamp that's encrypted with the session key for communication between the client and the ticket granting server, and the requested lifetime, maybe 8 hours rather than the 24-hour lifetime of the ticket. And it sends this to the ticket granting server. Now the ticket granting server checks, do I understand, do I know about these various different principles? And it goes ahead and it generates a session key for client to service session communication. It also extracts the database server's key. Right? It then creates what's called the service ticket. And this contains that session key that it just generated, the client principal name, the ticket lifetime, 8 hours, KDC timestamp, client's IP address, and it encrypts all of that with the database server's key, right? Or database services key, thereby forming a ticket or token. It then adds the client's copy of the session key, the service principal name, and the ticket lifetime, and it encrypts that with the client to ticket granting server session key, and then sends that all back to the client. Now, the client then decrypts that. It places the service ticket and the related decrypted session key into its credential cache. Now, the client needs to turn around and talk to the database, and it sends the service ticket to the service, and the database service decrypts it using its key. Remember, that service ticket is encrypted with the database services key, and it gets out the client's principal name and the session key that they're going to use. All right? Now, how the client sends the service ticket to the service isn't defined by Kerberos, and it can vary from application to application. Because, for example, database clients talking to database servers use a database server application protocol, and so the application protocol has to be, quote, Kerberized, under quote, unquote. And that means you have to make that application protocol aware of Kerberos. Okay? And there's some alphabet soup we'll look at in a few minutes that comes in at that point. So notice, Kerberos authenticates the clients and services to each other, but it says nothing about authorization, right? What you get access to, which database schemas you get access to, which tables you get access to, etc. That's all controlled by the database itself, right? It's nothing to do with Kerberos whatsoever. So in our complete example, you can see there's the step 1, user login. In step 2, there's the AS request message. Step 3, AS reply. And the client's able to decrypt the AS reply and extract the ticket granting server session key, etc., and the ticket granting ticket, because the user gave the correct password. Or maybe he didn't, in which case the whole thing just stops at this point. You can't make any further progress. Okay? Now, in normal operation, if this is all working correctly, what happens now is the client caches the ticket granting ticket. Then when it wants to connect, okay, in step 5, it sends a ticket granting server request, gets back a ticket granting server reply containing the service ticket, okay, caches that locally, then sends it to the database, and they can then now communicate. Notice that if you want to talk to another service, you don't start with step 1, okay, you actually start from step 5. You've already got a ticket granting ticket that's good for 24 hours, so as long as it's good, you just make further requests by using that ticket granting ticket session key to actually communicate and send ticket granting server requests and get back replies, etc. So it doesn't go back to square one. Now you might notice a vulnerability in this protocol, which is that in step 2, the authentication server request message is unencrypted and doesn't in any way authenticate the client. What authenticates the client is really step 3 and step 4, when rather than asking the client to prove that it's given the right password, instead the authentication server sends back some information which is only useful if it's encrypted, if the correct key was created in response to the correct password. But all these AS replies are encrypted using the client's key. Okay, if you go back and look at step 3, okay, this is all encrypted with the client's key. So what a bad guy, an attacker, could do is to force the authentication server to generate lots and lots of ciphertext, lots and lots of messages in the form of AS reply messages. And by getting more and more ciphertext to work on, could eventually break the client's key. Okay? To avoid that, what may be required is what's called pre-authentication. And in pre-authentication, what happens is that the authentication server, when it gets the AS request message, says, oh no, stop right there. Instead, do pre-authentication. And that requires the client to take a timestamp and encrypt it with its key and send it to the authentication server. The authentication server decrypts it, checks it's a valid timestamp, and then they can continue with the AS request, AS reply from that point onwards. Now I mentioned that in step 8, the client communicates to the database server, typically using some database protocol, which must be Kerberized to carry the tickets. And there are various protocols that are used for this purpose. Things like GSS API, SPN EGO, which is Simple and Protected Negotiation, which has been implemented in abstract syntax notation on Windows, but last time I checked there wasn't implementation on Unix. There's a thing called SASL, which does exist on Unix and can in theory wrap SPN EGO and also GSS API. There's an implementation called Cyrus SASL. And then there's the Microsoft Security Service Provider Interface, which you can make protocol compatible with GSS API. What this means is that in very heterogeneous environments, like a mixture of Unix and Microsoft and what have you, you typically wind up having to do some plumbing work. It's as though you've got plumbing in which some of the pipes have got imperial measurements, inches, others are metric, measured in centimeters. Some have got right hand thread screws, some have got left hand screw threads, and you've got to make your own adapters to couple things together. And most companies wind up at some point trying to wire these things together, and they write code to connect things. Very often they have to do a lot of playing around and experimentation to get it to work. Their code is actually pretty ropey and the result of lots of experimenting, and it's got unused blocks of code in it and what have you. So I know, for example, I have a client that's one of our big 4 banks. They've got a lot of Kerberos internally, as well as Microsoft Active Directory, and they've written code to make it all interoperate, but there's no way they're going to release that code to anybody. It's pretty shocking stuff. Now remember that Kerberos uses symmetric or secret key crypto only. It originally used DES, it can use AES or anything else these days. What happened when public key crypto came out? Well, somebody actually did come up with an extended version called SESAME, from the phrase Open Sesame. I think the name came first, and the acronymic expansion, Secure European System for Applications in a Multi-Vendor Environment, came later. Essentially, it's a single sign-on scheme. Distributed access controls using both symmetric and public key crypto. The user authenticates to an authentication server, which returns a token rather than a ticket. and the user then presents the token to a thing called a privileged attribute server, rather than a ticket granting server, to obtain what's called a privileged access certificate. And that contains access rights and capabilities, as they're called, which is yet another topic. The user can then take the privileged access certificate and pass it over to services as required. It can be made interoperable with Kerberos version 5. Now, what about authentication using public key crypto? Well, authentication is much easier with public key crypto. I mean, for logon authentication, for example, right, we can solve the problem by asking the person logging on, or the software they're running, to encrypt a nonce with their private key. We can make it a little bit more complex. We can include things like session IDs and timestamps into this, for example. We could send a challenge to the logging on machine/person and get them to encrypt the nonce with their private key. And we then decrypt it with their public key, get back what we sent. Hey presto, that provides session entity authentication, logon authentication. We've already seen how we can do message authentication using public key crypto. That's digital signatures, right? But does it really provide authentication? Excuse me. It leaves us with a $64,000 question. I've got this public key that you claim is yours. How do I know it really is yours? I mean, you could say to me, in an email, my name is Donald Trump, and I'm going to authenticate messages to you by using private public key cryptography. And you can get my public key by going to www.whitehouse.com. Okay, does that prove that you really are the genuine Donald J. Trump? I don't think it does, right? Because how do we know that www.whitehouse.com is real? I mean, don't try this at home, boys and girls, because the real White House, of course, is www.whitehouse.gov. It's a US government institution, so it's in the .gov top-level domain. And last time I looked, I didn't look, but I checked, www.whitehouse.com was actually a porn website. So, it doesn't really prove very much. This thing that I've given you as a public key, do I know it's yours? I don't really know. One scheme that was discussed in the previous lecture was having some kind of trusted third party maintain a directory or registry or white pages that contains your name, your public key. And I gave the example earlier of Lotus Notes, which works that way. It actually has the public key stored in a central name and address book, as it's called. It's really a directory for the organization. But another way of doing it is this. I would believe that that public key really is yours if I get a message from somebody that I trust. And that message contains your name and other identifying information and your public key. And that entire message is signed by them. And I trust them. And I have their public key already. Then I can use their public key to check the signature on the message that they sent. If it verifies correctly, then I know that message has not been tampered with. It was sent by someone I trust, and that it does contain the name and the corresponding public key. Okay? And there's a special name for that kind of message. We call it a certificate, a digital certificate. And the someone trustworthy is actually what we call a certifying authority. Now, we'll talk more about certifying authorities in the next lecture on network and telecommunications security. But right now, I just want to introduce some general concepts. In the case of X.59 certificates, okay, which is the format of these messages that contain a public key and identity of a principal, you trust the certifying authority in terms of its integrity and its competence to identify a principal and correctly generate these messages and sign them, etc. And it is benevolent. The certifying authority confirms the identity of the principal and the matching public key. Can you trust the principal? You pretty much have to. But there may in fact be, as you'll see, a hierarchy of certificates, because the CA, the certifying authority, needs its root private key and the corresponding certificate that it has to last for a long time, typically decades, so it can't use it to sign too many certificates. Therefore, it will periodically generate a private public key pair, create a certificate for that public key, and then use the root private key to sign that intermediate certificate, and use its corresponding private key to sign other certificates. And we'll see this in more detail in the next lecture. But actually, can you trust them? Well, as Matt Blaze at AT&T says, commercial certifying authorities will protect you against anyone that they refuse to accept money from. It's all about the money, really. Now, there's an alternative scheme called PGP, and you're going to get a chance to use PGP, and you're also going to get a chance to go and get Next.59 certificate as well in the workshops. PGP, pretty good privacy. It's actually developed by, who was it? I'll come back and remember it later on. Back in the early 1990s. It uses what's called a Web of Trust model. Now, the trustworthiness of a public key, in PGP, people sign each other's public keys. So the public keys are any kind of certificate that may be signed by multiple different people. And your view of a public key is that you may view it as being undefined in terms of trustworthiness, or marginal. You might say, well, it may be valid, or complete. If it's complete, then you're confident the public key is valid. But the people that sign other keys are called introducers. And the big question you have about them is, how well do they understand the implications of key signing? Okay? It might be you just don't know them. You don't know how good they are at doing this kind of stuff. Then there might be somebody you know who's just a total flake. They'll sign anybody's public key without checking out whether this person really is that person or not. In which case you might assign them a trustworthiness of untrustworthy or none, no trust. Or it might be marginal. You might say, well, they're okay as a person. They don't really understand all the implications of this. If they sign someone else's public key, it's probably okay, right? But we don't know for sure. Then there might be someone like me, of course, who is fully trustworthy. I do understand the implications of signing keys. I don't sign people's public keys unless I've confirmed their identity properly by looking at their passport, photographs, driver's license, other credentials. And then when I do get their public key, I know it's their public key, and I sign it knowing their identity. So that's full trust. Okay. Now you're going to get a chance in the workshops to use key management software. You might use Enigmail, which is the thing we're going to use to sign emails, for example. You may use Cleopatra, or you may use the command line PGP command if you want to do that. Now, the trust evaluation algorithm basically is used by the software that uses PGP to work out whether or not you can trust a signature or not. And it basically says, if a public key is signed by someone you trust completely, then you can trust that public key. If it is signed by people you have marginal trust for, okay, in other words, they don't fully understand the implications or they're not technically competent, then you might require, in the case of PGP, the commercial PGP, you might require 2 marginal signatures. GPG, the GNU Privacy Guard, is actually a bit stricter. By default, it requires that at least 3 marginal people have signed a public key before you'll trust that key itself. And this just basically is an algorithm that says all of that. So, for example, you trust Alice. Alice trusts Bob. Bob trusts Carol. Carol trusts Dave. You trust Ed. Ed trusts Fred. Fred trusts Dave too. Now, how do you know that? Well, because Alice signed Bob's public key. Bob signed Carol's public key, and so on and so forth. But can you trust Dave? Well, that depends on whether you fully or marginally trust, let's say, Carol or Fred or, whatever. If you trust Fred and Carol marginally, okay, that's 2 marginals. If you are running PGP, you probably would fully trust Dave. If you're running GNU Privacy Guard, you might not. If you fully trust Carol, then that's enough, right? And so on and so forth. Now, one other sort of side topic is single sign-on in the enterprise. The idea is that in very heterogeneous environments with a range of different systems, like, for example, mainframes, mini-computers and mid-range systems like the IBM I-Series, etc., IBM P-Series, AIX Unix, other mini-computers and supermicros, PC networks based on Windows. We even in the past had things like Novell NetWare, which still lives on in many organizations, including Macquarie Uni. You'll often find that you have multiple different identities and maybe even different passwords on different systems for the same identity. That can make it really confusing for many people. They change their password in one place, then try to use the new password in a different place, and it still knows the old password. And that can really get complicated. So single sign-on schemes, okay, replace all these multiple sign-ons. In some cases, what they've done in the past is to use scripting and screen scraping. So when you change your password, it runs scripts that go out and log into various different systems and go through the password change procedures, right, to actually change your password across all the various different systems. And that makes life a lot easier for the user, and it simplifies access control generally. It also means there's no need for users to go around one by one, change their password everywhere. And you can often apply inactivity timeouts and failed login thresholds at the point of entry. But the downside is you typically are using the one password everywhere. And that is a weakness. If the password hashes get retrieved from one system and broken by a dictionary or rainbow tables attack, then it's compromised on every system. It's only as strong as the weakest link. And also cross-platform implementation may be difficult or impossible. There are obscure systems that just don't fit in with a single sign-on. So what's increasingly commonly used is federated identity management. And that works in many cases both inside and also between different security domains. A good example of this is if you go around the Sydney Morning Herald and the Guardian and other systems, and you can often log, because you often are, isn't everybody logged into Facebook all day, every day? Since you are logged into Facebook and Facebook has authenticated you, you can often get Facebook to vouch for you. So when you say, I want to log into the Guardian using my Facebook ID, we can use some JavaScript under the covers and some AJAX-style coding to actually exchange information between the Guardian and Facebook and have Facebook vouch for your identity and log you in. So this is sponsored by organizations like Facebook, Google, PayPal, Microsoft, and others. And I think the reason why is very obvious. I mean, once you've used your Facebook account to log into, let's say, the Guardian newspaper, the Sydney Morning Herald, other websites, Facebook now gets to know about what you're doing on those sites as well. So for targeting advertising and doing behavioral analysis, right, federated identity management is just a gift for companies like Facebook and Google, to a lesser extent PayPal, Microsoft, etc. But it's also used in web services, UDDI, SOAP, etc., right, where we would use federated identity management. And also there are protocols like OpenID, for example, which works this way. Now, the one that's most commonly used is a thing called OAuth 2, which provides an access token that grants access to a resource. It's not primarily an authentication protocol, it's a resource access protocol, but in practice it's very often used for authentication as well. A good example here is, suppose that you have a big family occasion like silver wedding anniversary, son's 21st birthday, whatever. Big party, everyone's taking photographs, and afterwards they're sharing them via Facebook or whatever social media service. But let's say that grandma wasn't able to make the party. She's in isolation in an old folks' home or quarantined with COVID-19 isolation, whatever, or just couldn't travel to be at the party. And then somebody has got a really nice photo of the birthday boy on Facebook. To get that photo to grandma, who doesn't use Facebook, you want to print it off. Now, at one point you might have downloaded the photo in a high resolution version to your desktop machine and then used an inkjet printer to print off a colored copy. But nobody does that because inkjet printers are rubbish. Essentially, inkjet printers if you don't use them continuously, which is very expensive, you don't use them for a while and the nozzles clog up. And so, you've got to use them a lot, which becomes very expensive, or you just don't use them at all, in which case you can't print off one photo. So what you want to do is use a photo printing service on the internet and have them print the photo and post it either to you or direct to grandma or whatever. So how can you do that? Well, you could give the photo printing service your Facebook password. You have to be totally clueless to do that. Instead, what you want to do is give them access to just that one photo. So they can access the one photo, download it and print it, but they can't access anything else in Facebook on your account or anybody else's for that matter. That's what the OAuth 2 token system does. Okay, you can generate a token which is passed over to the photo printing service, which gives them access to just the photo alone. They can present that token to Facebook, and that will get them back the photo. They can then do what's required, print the photo, post it to grandma, etc. There's a similar kind of protocol called Security Assertion Markup Language, or SAML, which is specified in XML. Most of the ones we talked about so far use JSON, the JavaScript object notation. But this one's based on XML. And again, user requests a service. The service provider requests an identity assertion from the identity provider. The identity provider is Trent, the trusted third party. It is the KDC. It is the service like Facebook or Google or whatever. Right? So SAML can be used for mostly its internal services. So an example of this, I'm actually using right this moment a thing called Camtasia from TechSmith to record and edit videos. And if I go to the Camtasia TechSmith website, you can see that I can either log in by creating an account with some third party called GetSatisfaction, and have to think up a password, a different password from every other password, and then save that password in my password safe, or write it down if I don't know how to use a password safe. Or I can just log in with either my Facebook account or my Google account. So guess what I do? I log in with my Google account. And in fact, you probably have realized this, and I certainly rely upon it for some students. You can log into a lot of different sites using your Macquarie Uni student email account, because it is a Google account. It's a Gmail account. So when it says log in with Google, you can log in as student name at students.mq.edu.au, and you don't need to give the site your password. From a site developer perspective, this is great, because when I go to the TechSmith site, I haven't actually got a password on their site. They haven't stored any password hash on that site. If it's breached, there's no way that the hashes can get stolen, subjected to a dictionary or rainbow tables attack, and then used to compromise my credentials anywhere else. So I am safer. It's more convenient. Once I've logged into Google, I can just say sign in with Google anywhere, right? And it makes life a lot easier.